Hello everyone, my name is Sachin Kothari and today I'll be presenting my second lab report, Lab 2, Motion of a Falling Object. In our last lab report, we analyzed an object moving with a constant velocity, in which we found out that the net force was 0, making this entire side 0, making the final equal to the initial velocity. This time we're actually going to have two forces adding to a net force, so the object may or may not be at a constant velocity. The two forces that add up to be our net force today are the weight force and the turbulent drag force. What is the weight force? The weight force is the force that pulls the object towards the Earth. It is equal to the mass times the gravity times j hat, which is the direction that the object is falling in. Because the object is in free fall today, the gravitational acceleration is going to be negative 9.8, which is why I have the negative outside. The drag force, which is the force that pulls the object away from the Earth, and is caused by the resistance of air, is b times the magnitude squared times the cap, and in this lab we were instructed to use the turbulent drag, in which the object's magnitude is proportional to the square of the object's speed, which is why I have the square there. The faster the object is falling, the more the drag force. So now let's look at my tracker. My system was a coffee filter today, and everything in my apartment was the surroundings. So you can see my object fell down the negative y-axis, with this being the positive y, this being the positive x, and this being the negative x. From tracker we obtained my initial position, the final time, and the final y position. And we kind of have an idea of our experimental graph here, which I'll get to later. Let's look at my code. In my code, I plugged in the mass. It was approximately 1 gram, which is 0.00099 kilograms, which was the mass of the coffee filter. The initial position we got from tracker. The initial velocity was 0, 0, because the object was at rest in my hands before I dropped it. We scroll down to my to g, which is equal to 9.8, which is basically the acceleration from the weight force formula. We have j hat, which is the direction that the object is falling in, and even though it choose up as the direction of the pulse y, and it's 1, it's actually going down, and I'll show you that it goes down because of the negative later on. B is my drag coefficient, and what drag coefficient is the b that we saw in this formula over here, and it's directly associated with the surface area. The larger the surface area, the more the drag force. And so we go down here, my calculation loop. This is the final time loop that we got from tracker. Here's the weight force formula, the mass times g times j hat. Here's the drag force formula, times the magnitude. There's two magnitudes indicating that it's squared, the j hat and the drag coefficient b. These two add up to be w plus fd, which is the f net. And here we have Newton's second law and the position of the ball. Arrow scale I calculated the same way we were taught to in the videos, with 2 divided by mg, with 2 being in meters, and that's how I got my arrow scale. If we run this code, see how it looks. My b value gave me the final position that I got from tracker, which was negative 2.285, and you can see it right here. So that means my b value is correct here. This is how my object looks. The yellow arrow represented the weight force, the b represented the drag force, and this is my model graph. Here it's pretty straight, and I'll get to that in a minute when I compare all three of them together. So now let's examine my code with no drag force, just gravity. And the entire code is the exact same, except that I took out the drag force down here. And I did that by hashtagging b here, and I basically took out the drag force down here. Everything else is the same, including the arrow scales and everything. Let's see how this looks. And what this is going to do is just fall straight down. The graph this time is nothing like the last time. It's not pretty linear. It keeps going down. It keeps going down. You know, just velocity is much higher than last time. Let's compare all of my graphs together. The dashed line is the model position. The red is the experimental. The B is the position with no drag. My models with the drag are actually really close, indicating successful experiment. This one had a very high velocity compared to these two. Not very high, but it's higher than these two. These had a slower velocity. And because they're straight, that means they're actually linear, which means they probably reached terminal velocity, which terminal velocity is when the weight and the drag force cancel each other out, indicating that there's no net force and the object is falling with a constant velocity, similar to like what we did in the last lab. So let's answer these two questions. Which models predict a terminal velocity? Discussed briefly, which I kind of just did, but we can go back to it. The objects fall in a straight line here. The slope is linear, steady, and that indicates a terminal velocity. So with the drag and the weight force, because the coffee filter was light in weight and was kind of the air kind of goes through it, the object falls really straight and it has it reaches a terminal velocity. Now the second question asked, imagine if the object was thrown down, would the terminal velocity in this case be different or the same if it was initially dropped, compared to when it was initially dropped, right? So it would actually be probably the same, except when you throw it, it's going to have much higher drag force, making the object decelerate at first, but then it will reach terminal velocity just like the other. So it probably reached terminal velocity a little earlier because there's more drag force. It actually depends on how fast you throw it too. Overall, the experiment was very successful, and thank you for